Hello everyone, welcome back to the channel Code with AKJ. Today is day 55 of solving Geeks for Geeks problem of the day. And today's problem is a classic interview problem, that is search in rotated sorted array. So the question says given a sorted and rotated array ARR of distinct elements, the task is to find the index of a target key. Return -1 if the key is not found. So we'll dive into both brute force approach and optimal solutions. So let's get started. So here's the question. We have given a sorted array that's been rotated at some point, and you need to find the index of that target key. And if the key isn't found, we'll return -1. So let's understand this example. So given array 5, 6, 7, 8, 9, 10, 1, 2, 3, and the given target key is 3, and we need to find this given element key in our rotated sorted array, and we need to return the index of our target key. So in this case, the target key 3 is present at index 8. Coming to the second example, our target key is 6, which is obviously not present in our array, so we'll return -1. In our third example, our target key is 42, which is present at index 1, so we return index 1. So let's get started with our brute force approach. So here the simplest way is to iterate through the array of elements, and we'll compare each element with our target key, and if found, we'll return that particular index, and if it is not present in our array, we'll return -1. So let's quickly code this brute force approach. So we'll take the size of our array. We'll use our for loop to iterate over this array. We'll compare each and every element with our key element, and if it matches, we'll return that index. And after finishing our for loop, if we didn't found our target key element in our array, we'll return -1. So let's quickly compile and run this. So let's submit. So this approach is straightforward but has a time complexity of O of n, as we are iterating through the entire array. While it works, it's not efficient for larger array. So time complexity for this approach would be O of n, and space complexity of this approach would be O of 1. So let's try to optimize this approach and bring down our time complexity. So in our optimal approach, we'll try to use the efficient method, that is modified binary search. So since the array is sorted and rotated, we can leverage its properties. So the key idea of our optimal approach is to identify which part of the array is sorted, and then decide to search on that sorted array. So since this given array is rotated and sorted, we need to find a point where the array gets divided into two different sorted arrays. Our first step would be to find that particular index. We call that index as pivot index. So our initial step would be to find that pivot index, and which generally divides the array into different sorted arrays, and based on that index we'll try to search our key and we'll return the particular index. So let's quickly understand our optimal approach where we are using binary search, and our initial step would be to find that pivot index, where generally divides the whole array into different sorted arrays. So in this case, that particular index would be the value 10. So this particular index would be our pivot index, where generally it divides whole array into different sorted arrays, that is from 5 to 10, and another would be from 1 to 3. So after finding this pivot index, we'll search our key based on its value, whether it present in the first array or it is present in second array. So in this way, we'll search our key in our array A. And since we are using binary search, the time complexity of this approach would be O of log n, and space complexity here would be O of 1. So let's quickly code this approach and let's submit. So let's code our approach. So initially, our first step would be to find that pivot index. I'll use a function called getPivot, and I'll pass my array with its size. And we'll check on which part of this given array our key exists. So if key is in between the range of array of pivot, we can say that the key exists in the second half of our array. So we'll search using a function binary search, where we'll send the index starting point and the ending point along with our array and key. So if it does not exist in the second part of our array, we'll search in the first half of our array using the same function, sending our array and starting an ending pointer, which is 0 to pivot -1, sending our key value. So let's try to write our get pivot function, which takes a vector array and the size of an array. So we'll take two pointers, start and end. We'll calculate our mid. We'll run a loop till start reaches end. We'll check if the starting point is still less than the mid value. We'll keep on incrementing our start pointer. We'll update our end pointer with our mid. And again we'll calculate our mid pointer for next iteration. Okay, and finally we'll return our start point. So in this way we'll find our pivot index from the given array. Finally write our bsearch function, which will search a given target value in our array. It takes a vector and start pointer and end pointer and a target value. So we'll initialize our start and end pointer with the given parameters s and d. We'll calculate our mid pointer and we'll use a while loop until or unless start reach the end. We'll check whether the mid pointer matches with our target value or not. So if it matches, we'll return the mid pointer. If not, we'll check whether the target value is less than array of mid value. So if it is, we'll decrease our end pointer till mid -1 to decrease our search space in our array. And if not, we'll increment our start pointer till +1 to check in the other part of our whole array. So in this way, we'll check that given target value based upon our search space, whether it exists in the left part of the array or right part of the array by moving these two pointers start and end. And finally, after finishing our while loop, if we found our target value, we'll get our mid pointer, and if not, we'll return -1 from the function. So in this way, we'll first find our pivot index, and based upon that pivot index, we'll check whether this key exists in left part of the array or right part of the array using our bsearch function. And finally, we'll return that index of our target element if found, or else we'll return -1 if the key is not found. So let's quickly compile and run this. Okay, so let's submit. As you can see, this solution also got accepted, but here the time complexity would be O of log n and space complexity would be O of 1. So let's quickly analyze the time complexity and space complexity of both the approaches we have discussed so far. So for our brute force approach, which was pretty straightforward, the time complexity was O of 1 as we are iterating over the whole array and searching that key element, and space complexity was O of 1. And coming to our optimal approach, where we have used binary search, here the time complexity would be O of log n and space complexity would be O of 1. And that's it for today's problem. I hope you found this explanation helpful. So try implementing both approaches and let me know your thoughts in the comments. So don't forget to like, share and subscribe for more daily coding solutions. I'll see you in the next video. Keep coding and keep growing. Thank you.